Okay, lesson 12.1 is the triangle proportionality theorem. We're going to be covering that real quick. Here is the theorem. Basically, it says that if you've got two parallel lines and one of them crosses through this triangle, and these two lines are parallel, as you can see given by the symbols, then that means that these triangles, the big triangle and this small triangle, are proportional to one another. Go ahead and pause the video and write this down if you need to in your notebook, and then hit play when you're ready to resume. This is actually proving the triangle proportionality theorem. We're not going to go over this proof. However, you can pause the video and write this proof down if you need to. If it's a little unclear, I'm going to zoom in here just a second to the top portion so you can copy that down. Go ahead and hit pause. And then there's the bottom portion. And now we're going to get on to actually applying the triangle proportionality theorem. So in applying the theorem, again, we have these two lines, XY and BC, are parallel to each other, as you can see by the symbols. We need to find the length of CY. We know this length and this length and this length, but we need this length, the entire length here. So the first way we're going to do it is we are going to find CY by stating that AX is to XB as AY is to YC. In doing that, we just substitute the numbers in. We know that AX is equal to 9, and XB is equal to 4, and AY is equal to 10. So we just do a direct substitution, and then we're going to cross multiply 9 times our variable, which is YC, times 4 times 10. And we are going to go ahead and pause the video if you need to and work out the algebra. And then divide both sides by 9 and come up with the distance here of CY, which is actually 4 4/9. Okay, our next one, number 2, we're going to find the distance PN here. And again, using the triangle proportionality theorem, we can deduce that NQ is to QM as NP, or PN, is to PL. And again, substituting the numbers in, we've got NQ, which equals 5. We have QM that equals 2. We have PN that we do not know this time. And LP, or PL, we know is 3. So again, we can cross-reduce this and cross-multiply just like we did above. Again, remember to cross-multiply. We've got 5 times 3 is 15. We got 2 times PN equals 2PN. And then dividing both sides by 2, we come up with PN is equal to 15 halves, or 7.5. Okay, now it's your turn. You got two triangles here, triangle EFG and triangle MNP. Sorry. Anyway, what you are going to find in the first triangle is we need to find the distance DG. You need to find DG, which is this section right here. And in number 4, you're going to find RN. So go ahead and pause the video, work out these two triangles according to the triangle proportionality theorem, and then hit play or resume when you are ready to reveal the answers. And there she blows. Again, setting it up as the proportion, filling in the numbers, solving for x, or in this case DG. 960 divided by 32 is 30. Same way with this one. Setting up the proportion, M is to R, or MR is to M, or RN, as MQ is to QP. Substituting the numbers in, solving for x, or in this case RN, cross multiplying and coming up with 6.25. And now part 2, we've got the converse of the proportionality theorem, which states that if you've got two proportional triangles, then you've got a line that divides the two sides, and you said that these triangles are proportional, then you could say that these two lines are parallel. So go ahead and pause and put this theorem in your notes, and go ahead and resume when you get ready to look at the theorem. All right, and if you want to look at the theorem, here's the proof of the theorem. Again, we're not going to go over the proof. Here's step 1, if you want to pause and write it down. And then step 2. And that proves the converse of the proportionality theorem. But we are going to focus on applying the converse to real situations. Okay, so applying the converse of the theorem, now we're going to prove that the lines are parallel. Before, we were given that the lines are parallel and we had to find a missing segment. Now we've been given all the segments, now we have to prove that M, N, and KL are parallel. So again, we set that up the same way. We do 42 is to 21 as 30 is to 15. Now, without having to cross multiply, you can recognize that 42 divided by 21 is 2, and 30 divided by 15 is also 2. Therefore, if 2 equals 2, then that proves that because these segments or these triangles are proportional, then those lines are parallel. Another way to do it is to just say that JM to MK is equal to 42 over 21, which is reducible to 2, and that Jn, Jn and NL equal to 30 over 15, which is also equal to 2. So either way you go about it, you can get there the same way. And therefore it is proven by the triangle proportionality theorem, or the converse. Of the triangle proportionality. All right, moving on to our next example. So now, we're missing these line segments here. We're to prove that DE and AB are parallel, but we're not given this length or this length. However, we're given the entire length of AC. So the entire length of AC is 36, and the entire length of BC is 27. If we take 36 and subtract 20, then we get 16. So this segment's going to be 16. If we take 27 and we subtract 15, then we get this side of 12. Now that we've deduced that, we can go ahead and set the same thing up. Again, you've got 20 over 16 is equal to 15 over 12. And again, you can reduce these down and realize that 4 goes into both of these. 4 goes into 20 5 times, and 4 goes into 16 4 times. And 3 goes into both of those. 3 goes into 15 5 times, and 3 goes into 12 4 times. So we can already see that these proportions are proportional. But we can also set it up like we had done before and said that CD to DA is going to be equal to 20 over 16, which is reducible to 5/4. And if you want to say it's even, reducible to 1 1/4 or 1.25. And then we can also say that CE to EB is 15 over 12, which is also reducible to 5/4, which is reducible to 1.25. And because these are proportional triangles, that makes DE, even though it doesn't look like it here, again, we're proving by the numbers, and I did this a little slight just so you'd say, oh, well, they look parallel, because these look parallel, but these don't. Again, looks can deceive. I did this on purpose, but proving by the numbers, therefore, because these are proportional, therefore we can say that DE and AB are parallel due to the converse theorem above. Okay, now it's your turn. I want to also tell you, it's not going to happen in this problem, but if we were to find out that these were not proportional, then we cannot prove that those lines are parallel. Just keep that in mind for future reference. So now it's your turn. I've given you all the line segments, which is like our example 5 above. So go ahead and pause the video, work that out, set them up as proportional triangles. If they're proportional, then the lines are parallel. So go ahead and hit resume when you're ready to review the answers. All right, 2 ways you could do it. Again, set it up as a proportion. 90 is to 72, as 67 is to 54. Cross multiply them, which we hadn't done in these examples up here. We just reduced the fractions. But if you cross multiply, 90 times 54 is 4860, and 72 times 67.5 is also 4860. So therefore, we prove that these are proportional. Or you can take the line segments like we did before and put them 90 over 72 is equal to 1.25. 90 divided by 72. 67.5 divided by 54 is equal to 1.25 as well. And 1.25 is equal to 1.25. So yes, RS and TU are parallel because of the converse proportionality theorem. And that concludes our lesson. And you can do the worksheets that are optional along with that. And if you have any questions, again, please email me.